Right, now that we've had a look at the angle between a line and a plane, let's look at the angle between two planes. All right, so it's really coming thick and fast here now, isn't it? But let's just take them one step at a time, do some practice, get the hang of it. It all comes back to the normals and back to finding the angle between two lines. We just need to find those two lines. And let's do that now for the angle between two planes. So I'm going to try and construct a pair of planes here. And you get to watch at how bad I am at drawing. So there's plane 1, and let's take plane 2 out this way somewhere. All right, out he goes, and he's hidden in there behind this plane. Hopefully that's okay. And so what we're after here is the angle between these two planes, which would be right, this angle in here. That's an acute angle. There's obviously an obtuse angle as well. Well, there is if you can see these planes are extended through. There's an acute and obtuse if they pass through each other. Now, so that angle in there, well, that's the angle we're after. But actually, if we look at, I'm going to deviate. I'll take you on another little journey here for a second. If we have to just look at perhaps a cross section of two planes, let's say it's something like this, and maybe I'm trying to replicate this angle here as that angle theta. Well, that angle we can find that angle somewhere else. Let's have a look at, and yeah, you guessed it. It's hidden again in the normals of my two planes. So so if I construct a normal in here, I don't know if that's any good, but that's my right angles there. Now I have a 1, 2, 3, 5. I've got a quadrilateral in here, which and a pair of right angles here and here. So I've now got this angle theta has, I know that over here I've got 180 minus theta, which on straight lines gives me angle theta here. So what I have is the angle between the two planes is equal to the angle between the two normals to the planes. So if we can now go back to our planes and extract our normal vectors to those planes, then we will be in business. So if I've got the normal to this plane here shooting off in this direction, and the normal to the plane down here, I'll choose a different color perhaps my pink, shooting off in this direction here, then that angle there, theta, is replicated as this angle in here between the two normals. So if I call my this normal M and this normal here N, then I have now a way, I know I can find out my angle between M and N, because I know how to find the angle between two lines. So it's simply cos theta is equal to the dot product of my normal vectors over the product of their moduli. And again, I'm going to take the absolute value because I want the acute angle between those two angles, between those two planes in this case. Okay, so there we have it. So what we're saying is essentially that therefore, right, the angle between two planes, is equal to the angle between the normal vectors to those two planes. So we extract from the information we have about the planes, we extract the normal vectors, and then we act on those on those two vectors with our trusty arccos formula to find the angle between those two normal vectors, which in turn tells us what the angle between the planes is. So let's turn to an example. Okay, so an example where we've got two planes and we want the angle between them defined in these ways. Pi1's in Cartesian form, pi2 is in vector form. The obviously pi1 is more helpful. We can see visually straight away what the normal vector for pi1 is. So we can call this call him M, and so that is the normal vector for pi1 is simply 2, -1, 1. A bit of work to do though for pi2 firstly, so I would rather see this. So I've got a point on my plane which is defined by 1, 2, 0, and now come my direction vectors, defined by in turn alpha and beta and the coefficients thereof. So -1 alpha in the I direction, -3 alpha in the J direction, and I've got in the K direction I've got no alpha, so -1, -3, 0, and then I've got in the beta direction I've got another vector that's heading off as 1. I'm now just looking at my beta coefficients. I don't have a beta coefficient in here, so that's 0 and 2 in the K direction. So from this I can say that I have I've got two known vectors on my plane pi2, and so now what do I do with those? Well, I cross them, I cross product them to get the normal, or to get a normal vector to the plane pi2. So to find normal vector to pi2, what we do is take -1, -3, 0 and cross it with 1, 0, 2. Okay, so rule out the top line. -3 times 2 is -6. It's, as soon as you think you've got the thread rather than just observing, although you might find that helpful, pause and do is perhaps a more productive method of gaining traction with this work. So by all means, press pause whenever you like and work ahead, and then come back, and perhaps then my explanation has a little bit more meaning for you. Ruled out the top line, -6. Ruled out the middle line, working in the opposite direction, 0 minus -2, so I get +2. Rule out the bottom line, 0 minus -3, so I get +3. -6, 2, and 3. That now constitutes my normal vector, so I can call that, what's my color coding here? I think it's light blue for my my second normal vector, so I'll call that N. All right, so I'm ready to go now to find the angle between these two planes. So therefore, all right, theta is equal to the absolute value of m dot n over, all right, so this is arc cos the absolute value of the dot product of my two vectors, my two normal vectors m and n, over the product of their distances, like this. So that's equal to arc cos, now m and n are defined for me up here, 2, -1, 1, and I'm dotting with -6, 2, 3. So my dot product will be 2 times -6 2 times negative 6 plus negative 1 times 2 plus 1 times 3. That's all over the distance of m, the modulus of m, 4, 5, 6. So the square root of 6 by the square root of 36, 40, 49. Okay, so that all gets crunched, and we'll have a look at the result. Okay, so theta is equal to arc cos. What do we got here? Negative 12. So negative 12 minus 2 is negative 14, plus 3 is negative 11. Minus 2, yeah, negative 11. So that's going to be the absolute value of negative 11 over, now this looks like 7 root 6 down here. So now I can get rid of the absolute value signs and just call it arc cos 11 over 7 root 6. And now we just turn to the calculator, and we get 50.1 degrees, again to 3 significant figures. Please make sure you're getting in the habit of writing your answers to 3 significant figures. And all right, so now I think we're good to go with exercise 11.0, and we can do questions 3, 4, and 5. 3, 4, and 5. Okay, cheers.